Alright, continuing on with the component level review of my schematic. In this video I'm gonna start reviewing the ICs, but before I start I want to show you something that I did for the labels. So after I'm done with the ICs, I'm going to be reviewing the labels as well. And I wrote a script that helps me to export all the labels from the schematic, which looks like this. Let's see. Let's just maximize this. So I used group by in Python from itertools to group schematic labels by their name. I had to add a little bit of code here for parsing the schematic labels because the KiCad library utils by default did not recognize any label text. So what it did instead was just treat them all as text. But we can see, let's see here, we can see in the file that even though they're text, they also have a option here called glabel, and the text comes afterwards there. So I filter anything that has glabel that starts with where the description starts with glabel, and I place them into a separate list called labels. And I haven't made any effort to parse the direction of the label or anything like that. I know the directions of the labels are mostly wrong here on the schematic, so that's something that I have to take care of. But KiCad doesn't really care about that. The important thing is that they have the same name, and that anything that has the same name is connected together. Running this script produces a CSV file, but we can look what this CSV file looks like, and we can see that we output the number of occurrences of a specific label. And by just looking at this data, we can see that, for example, we have the VSA1 raw, which has 2 labels with that name. But then we have VSA2 raw that has only 1 label with that name. And already this shows that there is a problem on the schematic. And if we look at the schematic here, you can see that I forgot to name this part where this voltage sensing output goes to the amplifier up here. I forgot to name it on the second drive appropriately. So I have VSA2, and this is actually the output of the op-amp up there, so this is not desirable. This has to be named VSA2 raw instead, and this one as well. And this one as well. And if I save the schematic now and go to this script again, I can rerun the script, and we can see that now we have all these labels have 2 occurrences, which means that now they are correct. I'm not going to go through any more labels right now. This is going to be the next step, but right now I'll continue with the IC reviews. So let's look at our list of all of the ICs here. So the important thing with the ICs is to basically the same thing as with all the other components: check the package, but then also check the pins, whether the pins are connected correctly, and also whether the pins have the correct numbers. So it's a little bit more work than with most other components. But it's definitely worth it, because I'm pretty sure we'll find some problems with the ICs here. Let's see. So we have the MIC 2026. This is, I think, the USB, the chip that controls power. Let's see. I'm going to close this one, and it was a very useful technique to use group by. I haven't used that before, so that's very nice. Let's see. So we have this chip here. MIG 2026, it's so I see 8 and power supply voltage up to 5.5 volts. Let's see what we have here. 3.9 times 4.9. We can open the data sheet of this chip. So let's see. So U1. Let's go to U1 and just make sure that it has all the bypass capacitors and everything else that it needs. So U1 has the bypass capacitor there. This one is connected to 5 volts. We also have a possibility to bypass U1, and we have analog in power enable, analog in overcurrent. This is an output. And let's see what else do we have here. So this is flags need to have actually a pull-up resistor of 10K. So we should put pull-up resistors here. And this would be connected to VDD33 MCU. And then we have, let's see, load is connected there, and anything. What about the unused pins? Let's see. Supply filtering, 0.1 to 1 microfarad bypass capacitor, close to in. Yeah. Let's see. And I use a larger capacitor on the output there. I wonder if we need anything like that, because we do have bypass capacitors there, but we don't have anything. So let's see here. What happens if there is an overcurrent condition? Okay. This is highly unlikely. This will not occur in this situation because most, or actually it can occur. Let's see. No, I totally take that back, because we have this connected to the joystick outputs. So this can actually yeah, I think we need a capacitor here that is similar to to the one we have here. This 100 microfarads is probably a good idea. Or rather, no, let's scrap this idea. What I'm going to do instead is place capacitors on here. So I'm going to take this 2.2 microfarads and I'm going to place it here. Let's see. Maybe we can actually, now that I think about this, because I think that these ones have to be connected to VDD 5 volts actually, and not to the same supply as the joysticks, because if there is an overcurrent condition, we still want to have the op-amps functioning. Let's see, so we have this one will be 5 volts, and then obviously this one also needs to be. So yes, and also if there is any kind of over voltage fault here on the input, it will go to VDD 5 volts, which makes much more sense than putting it to analog in VDD 5 volts, because then it has basically nowhere to go. Let's see. We'll make it like this. And then we have the current limiter only for the analog joysticks, only for anything that is connected to this connector, the external devices. see. So got that, and then I need to just I'm just gonna add, I think I'm gonna add the capacitors actually here. So this would be our this would be 8 capacitors. 3, 4, 5, 6, 7, 8. And then all of that can go to this label. And I'm going to make this wire a little bit farther to the right so that we have place for the designators. Okay, and then we have the ground connection there. So these ones will go by the connectors. Let's just double check that we have all of the power connected correctly. It seems that way. And we have VDD 5 volts and analog in VDD 5 volts. And then we have the overcurrent input set to be a pull up to MCU. VDD 3 MCU. Alright. Is there anything else here that we need to think about? Let's see. $599, $393, and I think that, let's see, 394 times 493. That would be the footprint. 394, 493. Yeah. So the footprint is correct. But what about unused inputs? I think we can just leave them unconnected. Let's see. So definitely output B is unconnected, and enable B, right, we have to check the enable signal. Is enable signal let's see. I think it's active high. Okay, so there is both active high and active low, which is good to know. So 1 is always active high. And which one do we have? We have 1. So we have an active high enable signal. Shall we use an active high or an active low? I think that it would be very good to have a resistor here that connects. That's a no-fit resistor, but connects this power enable signal to VDD3 MCU. Just in order to have the possibility to enable this by default. Let's see. And this also provides kind of like a test point for this signal. Okay. Right, so it seems that I think this is pretty much done. I'm gonna go to other chips that have the same model. Let's see if we can find any other ones. I'm pretty sure there was more than one. There, U25. Let's see. Can we search for MIC 26? Yeah. So it's U25. I'm gonna add the resistors here. So we need 10K resistors. Let's see, to VDD3 MCU. Okay. Now we have the bypass in there, but also I want to add this. So power enable has to be connectable to VDD3 MCU. Let's do like this. Let's do this a little bit simpler. Alright, and then we have VDD 5 volts and this VDD 1 and VDD 1 5 volts and VDD 2 5 volts. Great, but what I want to check also is, let's see here. Yeah, so this one is connected just like the op amps. This goes to 5 volts. Let's see. And then we have ENC VDD, ENC1 VDD 5 volts, and then we have the capacitor there, batch connector. So that's exactly as I want it. And then we have ENC2 VDD 5 volts, and that is also connected perfectly. Okay, I think we can greenlight this one. Yep. U10. This is one of these potentiometers, and this one is, let's see, I'm just gonna pick up the exact the exact product code is like that. Unfortunately, I've removed the ability to edit fields here because I wanted to kind of get rid of that habit of editing fields on the schematic. So I always edit fields in the component library in order to make sure that the same fields are applied to all of the instances of a component. Let's find this component on Mouser. Non-volatile 10K potentiometer, sounds good. I2C supply voltage 2 to 5 volts, 2.7 to 5.5 volts, and the package is TS-SOP20. Oh, something I forgot. Something that I forgot here. I forgot to check the pinouts of these power chips, just to make sure. Let's see. Where is this power chip? I think we have one here, one down here. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4. Enable flag AB. 5, 6, 7, 8 out. GND out B. GND in out A. Looking good. Okay. Now I can move on. Now I can move on to this potentiometer. So, first of all, pin out P3, A, Viper, B, 1, 2, 3, 4, 5, 6, HEC, SCL, SDA. Then G and D, P1B, yeah, P1B, P1 Viper, and number 10 is P1A. And then it's 11, P0A, and then Viper, P0B. Look at this, 11, 12, 12, 14. So it's like sometimes you can't even trust the data sheets. It's interesting. So okay, anyway, 14 is write protect, inverted. 15 is reset. 16 is ground. No, 16 is A1. 17 is VDD. And P2B is 18, and P2 Viper 19, and P2A is 20. So the pinout seems correct. Next, we need to make sure that any of the signals here are connected correctly. But I want to check the footprint first. So the footprint is TS-SOP. Come on. So anything that ends with ST is TS-SOP here. Yes, so this is TS-SOP. Where are the footprints? Okay. Interesting. $51.64 or 660 times 640. Let's see what this has. This does not look like the package that they specify, but it could also be, let's see, it could also be that they measure with the pins and not just the package itself, but it would be very nice if they provided a landing pattern for these chips. Lead TS-SOP. Let's make sure that this is correct. do like this. Right, and what is the distance between pins? That would be the C. So 590 is supposed to be the distance between the pins. Let's see, we're a little bit off grid there. We'll just see, make sure that this is like 596. Okay, so that's fine. And then the pitch is E. 0.65. So the whole let's see. Yeah, let's just check the pitch. Yeah, 0.65. And the Y1 is 145. Yep, distance between pads 0.2. Right. Okay. Seems like this is correct. So let's move on. Let's move on to the connections here. So pin number 1 is connected to 3v3, and then the wiper is connected to the input of this op amp. So this goes to the analog output. So this value will go between 3v3 and ground. So that's fine. Now, then we have the address. This one is set to address 0, so address A0 is connected to GND. A1 is always connected to GND on both chips. Then we have APSCL1, APSDA1. And we have the ground, and then we have P1B is also ground, and P1A is VDD383. And this one goes to the next stop. So same here, and then we have the write protect reset, and let's see what the datasheet says about reset. Okay, worst case at 1.8 volts. That was interesting, but I want to find the reset signal. And what is this? Let's see. Up to 12 volts. Wow. There is a power on reset. Do we have any? Let's see. Reset has a pull-up resistor, 16K. What is smart there? Let's see. Quick pull up, pull down. Cool. Okay. So this write protect pin should be, let's see. The question is, do we want this to be write protected by default? Or should we just wait for the MCU to come up? I think that I think I'll leave them as they are, because these are connected directly to the microcontroller, and the microcontroller will be able to specify the values for this. And then it's also possible to lock the GPIO configuration so that anything that is like, although in this case we don't really care, because in this case these values are going to be changed. The idea here is that these values can be changed very often. Let's see, so this one is P2A, wiper, and P2B, and this one is VDD33. Alright, I think this is looking good. I think this is green. So U29. VDD33, or count adjustment 2, ground. This one has A0 set to 1. We have SCL, SDA, GMD. That's 3, 3. Yeah. This one is wrong. This one would be inverted, which is not desirable. We should use the same configuration for all outputs. This would be LCD brightness. And A, B is a 0, and then write protect reset. Ground on A1 and VDD33, ground on B, and or current adjustment 1, that one is on 3, now then there is our current adjustment R78 and R79. Yeah, this is fine, and we have the bypass capacitor for this chip. So this looks good. I'm gonna green light that one as well. And the next on the list is U11. U11 is the CAN of D transceiver, or actually the CAN of D interface. The transceiver is just taking care of voltage translation, while this one is a kind of the interface. Let's see, kind of the protocol interface. So this is this comes in VDFN 14, which is DFN 14. Yeah, I have to double check that one. So let's make sure that the pinout is correct, and then make sure that the actual footprint is correct. So we have, let's see, let's make sure that, yeah, like that. So 1 is TX scan, 2 RX scan, 1, 2, 3 is clock soft, 4 is int, 5 is OSC2, 6 is OSC1, and 7 is VSS. Yes. 8 int 1, 9 int 0, SCK 10, SDI 11, 11 is SDI, and this is serial data input, so it's slave in, so it's master out slave in, so it's massive. Yeah. 12 is SDO, 13 NCS, and 14 VDD. Yes, this is looking good, and next I'm gonna check the DFN footprint. Oh, by the way, the pin, let's see, we have input output, yeah, seems to be correct. Input SCKSD, and CS is an input, and SDO is output. Yeah, VDD is power. Okay, cool. Next is the DFN package. Where is the landing pattern? Here. Very thin plastic quad flat no lead package. 4.5 times 3. 3 times 4.5. Okay. It looks like it's correct footprint, but I have to double check the measurements. So we have pitch 0.65, so we can take measurement here. Yeah, because we are a little bit off grid, we get 0.70, but it looks like we have 0.65, and there are, let's see, there are thermal vias. Let's make sure that we have all the measurements right first. 1.6 x2, x2 is 1.65, y2 is the length of this, yeah. So y2 is 165, which also tells us the size of the package. So we're going to get something that's a little bit smaller here than 165. Wait, let's see. 420. 420 or 430? Yeah, 425 for Y2, yeah. 165 is for the X, of course. Okay, and then we have the silk screen there. And that would probably be our see. That'll be the courtyard around it. This seems correct, but this is in the default library. I don't really want to move it right now. I'm going to move all the footprints for revision B into my custom library, where I can modify them and add any little details that are specific to a component. But for now, I'll just leave that footprint as is, and we're just gonna go to this chip here, and let's see, we have kind of DMOSI, that's correct, MISO, kind of DCS, kind of SCK. We have the SOF, which is start of frame, which is connected to the MCU. We have the interrupt, and we have the, actually we could place test points here. So this would make good sense to have a test point there. Let's see. And then we have the oscillator, which is a 20 MHz oscillator, that's correct. I've checked the capacitors before. We have the standby, also connected to STB, which we can place a small, let's see, I'm going to place a small test point there, because this would be useful. If for some reason this doesn't work, we can check that the transceiver is not in standby mode. And then, yeah, and then that's it. Then we have RX scan and TX scan. Wait. Damn. Damn, this is wrong. Damn, this is wrong. Let's see. See, this is what I mean. This is why schematic review like this is so important. TX scan, RX scan. Awesome. Now this is going to work. It wouldn't have worked if I didn't see this problem. This is so good that I'm actually reviewing this component by component. Okay. So I think I can green light this one. Let's see, it has a, does it have, yeah, it has 3v3, yeah. It has a bypass capacitor as well, which is this one, and this one goes to the transceiver. So yeah, I can green light this one finally. Alright, I'm gonna stop this video for now and continue with more of the IC reviews in the coming videos.